Welcome to an online module of FOR 375. Today we will be talking about some of the cartographic systems used in US cartography. This module builds on what we've done so far, and you will start seeing in practice some of the concepts about maps and map projections. In the United States, the main agency in charge of producing maps is the United States Geological Survey, USGS. USGS uses a variety of projections to produce maps. I believe that there are about 16 that are routinely used for producing different types of maps. Some are topographic, some are thematic maps. At the end of this module, you will find a link to the most complete publication of the USGS about these maps, the Snyder booklet. That booklet reports all the details and all the equations that are needed for all of these transformations from geographic coordinates to map coordinates for each one of these projections. I really invite you to have a look at it, not because I think that you'll be using pen and paper to do the calculation, but because it's a good exercise to realize the level of complexity that is involved in performing these transformations. By the way, the transformations might be complex, but today we just program that into computers, so everything is done automatically. We will look at just two of these projections today. The UTM projection that is used for the large scale, so as we saw last time, large scale means detailed topographic maps, and the Albers equal area projection that is used for some of the small scale maps. So those maps where we want to have on our display or on a piece of paper the entire country. Let's start with the UTM projection. And let's take a step back. We've seen the cartographic projections. We've seen the concept of having a projection surface. Could be a plane, could be a sphere, could be a cylinder, could be a cone that touches the Earth, and we project imaginary rays from the center of the Earth to this projection surface. And we did look at the Mercator projection. One of the oldest projections produces horrible distortions in areas, but it does have some very useful properties. Namely, it preserves directions. And I told you that it is the map that was largely used in the age of discoveries because it would allow you to cross the ocean keeping a constant angle. It would not be the line of minimum distance, but it would take you to your destination. Now let's do a variation on the Mercator projection. Instead of having a cylinder that is parallel to the axis of rotation of the Earth, we will have a cylinder that is perpendicular to the axis of rotation of the Earth. You see here in the figure. And you see that the map we obtain is a funny looking map with very little distortion along the meridian where the cylinder touches the Earth, and increasingly big distortions as we move away. It's a bit like we saw with the standard Mercator. It's not a desirable projection for the whole globe. What we want to do then is a little twist. What happens if instead of having a single projection using a cylinder that touches the Earth at one location, what happens if we keep rotating this cylinder and we have a series of projections, each one of them made by having the cylinder touching a different meridian? This is the basic concept of the universal transverse Mercator. The world is divided in 60 zones, each one is 6 degrees, 360 degrees, the total circumference of the Earth divided by 60, and each zone is mapped with an independent cylindrical projection. So instead of having one single continuous map, we have 60 maps, each one obtained with a separate cylinder. Okay, meet my cat. This is Oscar. This projection has very low distortion and is widely used for national cartography, and we use it also for satellite imagery. Later in the class, you will be using Landsat images. Those are distributed in UTM projection. It's interrupted, so we have this big trade-off. Larger areas, continents, are split across zones. For instance, Europe is 7 distinct zones, and if we were to put together a single UTM projection of the continent, we're not going to get something particularly good looking. However, as I told you, this is a projection mostly used for local maps, so it doesn't really matter. We rarely have a UTM map that covers an entire continent. We're more going to have maps that cover not even the area of a county. We will see an example in the lab this week when you will be given the UTM map of Moscow Mountain. This is a table containing all the UTM zones of the globe, all 60. You see that the US spans several zones as well. In particular, now I can have a nicer zoom. US includes zones from 10 to 19 for the continental US, plus the Alaska zones. Idaho is in zones 11 and 12. In Moscow in particular, we're in zone 1. In zone 11, sorry. This is a bit of a problem with Idaho. It's split into zones that makes it slightly more complicated to have a statewide cartography. We will get into that at the end of this module. And now you can meet the USGS topomap. This is the backbone of the US cartography. It's a map in UTM projection at a scale of 24,000. 24,000 means that 1 centimeter on the map is equivalent to 24,000 centimeters on the projection surface. So 1 centimeter, 240 meters. It's a rather detailed map, and you will be working with it in the lab. It covers the whole of the US at this scale. The footprint of each one of these rectangles is 7.5 degrees to 7.5 degrees. As a consequence, each one of these covers from 49 to 70 square miles. The area is not constant because the extent in degrees is constant. 7 minutes has not the same value at the equator than it has at the pole. We saw that briefly when talking about parallels and meridian. So going from the southern US to northern US, these 7.5 minutes become narrower and narrower when reported in equal area projection. The vertical dimension, though, stays constant because 7 minutes on a meridian at the equator have the same length of 7 minutes of a meridian at the pole. These maps, each one of these maps are known as quadrangles. So a USGS quadrangle is one of these 1 to 24,000 scale maps. So in this map, we have a variety of information, and the next module will be about reading these maps. For now, enough to say that there's 4 grids, all of those ticks and lines on the map. They correspond to 4 coordinate systems: a geographic grid, a UTM grid, a state plane grid, and the public land survey grid. We will cover today the meaning of all these grids. We'll talk about the state plane system and the US public land survey system. Here's the detail of the bottom left corner of the map, with the legend, the scale relative to all these grids, and you can see now the variety of tick marks and numbers. In the next module, we will focus on how to interpret all of this. The second projection that is used by USGS and that we will talk about in this module is the Albers equal area. It's a conic projection, so we use this imaginary giant cone that touches the Earth, and that's the surface on which we are projecting the land masses. And it's an equal area, meaning that if we measure an area on the map and we multiply that by the scale, we will have the actual area of the polygon we are looking at. This map has a low distortion in the area between the parallels that are used for the projection, so it's very good for mid-latitudes. It's used for conus the conterminous US by USGS, using 29.5 and 45.5 as the standard parallels. We are roughly at 45.5, by the way, so we are in one of the areas with fairly low distortion. The directions are reasonably accurate within a small region, meaning that you can use this map to get a general sense of directions, but you wouldn't want to use this for a detailed survey. For a detailed survey, you're better off using the UTM quadrangles. This is an example of a US-wide map. It's a thematic map done by USGS, the National Land Cover Dataset. It's a satellite-based map where for each 30-meter pixel of the US, we have a vegetation class assigned. As you can imagine, I told you that this is a map with relatively low distortions at this scale. We are not going to use this type of map to get accurate directions and to do accurate measurements. You don't want to calculate the distance between Moscow and Troy on this map, or even less so the difference between Moscow and, let's say, Florida. There's better maps for doing that. But if we want to have a general view of the entire United States, this is a map that is a good compromise. It reasonably well preserves angles, shapes, and distances. It's used widely also for satellite products. This is a satellite mosaic of the conterminous US from Landsat data, and this is an equivalent Albert equal area map of Alaska. Of course, it's done using different standard parallels, because otherwise we would have unacceptable distortions. I also want to talk about the Military Grid Reference System, MGRS. Anybody of you who's been in the military will be very familiar with this. It's increasingly used also for satellite data because it's a NATO standard and it's a fairly clever way of having a standard cartographic system for the whole planet. It's a combination of several layers. First of all, there is a big rectangular grid. It's called the grid zone designation. It's big rectangles defined on our geographic space, on latitude and longitude. Each zone is 6 degrees wide to correspond with the UTM zones. So we have 60 zones identified by numbers. And bands. The bands are going from the equator to the poles. and are 8 degrees high. Bands are identified by letters from C to X using no letter I and no letter O because they're easy to confuse with the numbers 1 and 0. Zone X is the last one and is the only one that is 12 degrees instead of 8. Letters A, B, Y, and Z are reserved for the polar regions. Then we have a second level of square grids. These are defined in UTM projection. It's a 100,000 meter square identification. So big squares of 100 kilometers by 100 kilometers. Those exist within each grid zone, and they're identified by letter for the column and a letter for the row. So columns go from A to Z, rows go from A to V, no I and no O. At the poles, the 100 meter square grid is defined in a different projection. It's in a polar projection. And finally, we have a numerical location, given the north and east coordinates relative to the bottom left corner of each square. The numerical locations can have different level of precision. And what is important about the GRS system is that rather than identifying a point, it identifies a square cell. This is now all very theoretical, so we're just going to play around. I found a nice app that lets you visualize the MGRS coordinates. We will do that for our classroom. So we're starting with a very zoomed out view of the United States, where we see the grid zones. As we zoom in, we start seeing these 100 kilometer cells. And we start seeing Moscow now. We are in the 11T grid zone, and we are in the MM cell. We will keep zooming in. See that Moscow is just at the boundary between two cells. Now we start having some finer grids appearing. Those are metric grids, so they represent our coordinates in multiples of meters. I'm trying to find campus, getting close to campus. U of I library, and here's Renfrew Hall, and I am putting the center of the cursor roughly to what I believe is the position of our classroom. We have the finest grid here. This is a 10-meter grid. Okay, so let's recap. Our classroom, we've seen, is in grid zone 11T square mm. The coordinates depend on the desired precision. The NATO standard is 10 meters. So if you have the coordinate of a cell and it's 4 alphanumeric characters for grid zone and square, and then we have 8 digits, that's 4 digits for the x coordinate for the east, 4 digits for the north, that means that the precision is 10 meters. If the numbers are 6 numbers, then it's a 100 meter grid. If you get only 4 numbers, it's a grid in kilometers. If we get 10 numbers, that would be the 1 meter grid, and so on and so on. This is a very convenient system because by the number of characters in the string, you immediately know what is the precision. And very important, when you go from higher precision to lower precision, there's never any rounding. The coordinates are simply truncated. So it's a nice system to go up and down in precision. And once again, it's not identifying the coordinates of a point, it's identifying the coordinates of the bounding square box of your point. Let's move to state cartography. First of all, the state plane system. So US-wide system consisting of 124 geographic zones using local state-defined reference systems. Depending on the state, it's in transverse Mercator or in Lambert conformal conic. The measurements are always in feet, and this is a bit of an antiquated system that was used for state cartography. In the case of Idaho, we have the Idaho State Plane System that is still used for some surveys and is still reported on the USGS quadrangles. It's in a UTM projection using the NAT27 datum, so a fairly old datum. The coordinates are expressed in feet. And we have 3 zones in Idaho, so there's 3 projections done with separate central meridians. Each zone is approximately 2 degrees wide. There's and they're termed East Zone, Central Zone, West Zone. We are of course, in the West Zone. There's inconveniences using this projection because it means that going from one zone to another, we change the coordinate system and we need to do a transformation. As a solution, a while back, the IDTM system was also introduced. It's a UTM projection, single zone, using a more modern datum, the NAD83 datum, and uses meters for distances. If you're curious to know more about the Idaho State Plane System and the IDTM system, follow this link